Okay, we're going to begin a set of video lectures on rational functions. And we're going to begin here by discussing their properties. Specifically, our objective, we want to identify rational functions, and we want to identify their domain. All right, what do we know? Well, we know what domain is when it comes to a function. Okay, the domain is the set of all inputs, the set of all values for a function. Those that work, those that can go into the function and give you an output. Okay, that's the domain. Now, we've talked about domain with fractions before, and what we want to watch out for when we're dealing with fractions is we want to watch out for zero denominators. And that's going to come into play in this video lecture because a rational function will have a denominator, ratio meaning ratio, which is a fraction. So we want to watch out for zero denominators. Okay, so what's a rational function? A rational function, again, root word ratio, which means we're talking about fractions. Okay, so it's the ratio of two polynomials. Okay, so for example, f of x equals p of x divided by q of x. This is a ratio of two polynomials. P of x and q of x are polynomials. And q of x cannot be the zero polynomial. This cannot be 0x squared or anything like that. You can't, obviously q of x cannot be 0 because then you're dividing by 0 and that doesn't work. So q of x is not 0 as a polynomial function. So as you might imagine, the domain is the set of all real numbers. We always start there and then we subtract, we take out. So the domain is a set of all real numbers except those for which q of x equals 0. Okay, we can't have a 0 in the denominator, so anything that results in the denominator function being a 0 is going to rule those numbers out of the domain. Let's take a look at a few examples. Think I'm high enough? All right. So here's the function, r of x. I think all the examples I just called the function r of x is equal to x squared minus 4 over x plus 4. Okay, this is a second degree polynomial in the numerator, and this is a first degree polynomial in the denominator. Okay, so obviously x plus 4 is not the 0 polynomial, but we need to make sure that we can't have a 0 in the denominator. So we need to look at it and say, wait a second, we know x plus 4 cannot be 0, okay, which means that x cannot be negative 4. So our domain, and I'll write it in set notation, all x's such that x is not equal to negative 4. Okay, that's the domain of this function. Let's take a look at the graph. Okay, I think you can see this here. I'm going to graph this one. I've already put it into the calculator. Okay, so here I am. Y equals x squared minus 4 over x plus 4. And I had to play with the window a little bit to see the entire function. So I went into the window and I chose x from negative 50 to 50. And I chose y to go from negative to 50 because the standard window wasn't giving me the entire function. So I played a little bit with it. Now let's press the graph. Well, there's your function. Okay, the function comes in from the left. Here, it's an increasing function to here. It gets close to negative 4, and then it drops because x cannot be negative 4. And then on the right side of negative 4, so negative 3.999, for example, the function is decreasing, it then hits the origin, and it becomes an increasing function again. So your rational functions might have some funky graphs. They might have graphs with gaps in them. Okay, rational functions are certainly not necessarily smooth and continuous like polynomial functions. If I were to say second calc value, I'm going to choose value. Well, what's the value of the function when x is -4? It's going to return nothing, okay? Because there is no value at x equals -4. It's not defined for -4 because it results in a 0 in the denominator. So there is, and we'll learn this in a next video lecture, in an upcoming video lecture, there's what's called a vertical asymptote at -4, okay? That shows, hey, -4 is not in the domain. Okay, let's take a look at another example here. R of x is equal to x minus 5 divided by x squared plus 2. Again, this is a polynomial function. The numerator is a first degree function or linear function. The denominator is a second degree function or quadratic function. Well, what do we know? All we care about is that x squared plus 2, our denominator, cannot be 0. Well, this is telling us that x squared cannot be -2, and in the real number system, this is never possible. And because our domain is the real number system, we're not worried about the fact that this has an answer that is an imaginary answer. We're going to say that we're in the real number system, and so our domain is all real numbers. Nothing happens. We're never going to get a -2. We're never going to get x squared to be -2 to make this a 0. I'll write this in interval notation. -∞ to infinity is that domain for example 2. Let's do a few more examples. Okay, I think I'm on there straight. Example 3. Let's take a look at R of x is equal to x squared minus 9 divided by 3. Okay, this is a polynomial function. The numerator is a second degree polynomial or a quadratic. The denominator is a constant polynomial. It's degree 0, if you will, but it's a constant polynomial. Well, there's no way here. There's no way our denominator is 3. It's never going to be 0. So again, and I'll use set notation for this one, all x's such that x is a subset of the real numbers is probably the simplest way to write that in set notation. Okay, how about example 4? Okay, our rational function, r of x, is equal to x squared minus 4 divided by x plus 2. Oh, we've already done something like this. Okay, even though the numerator is different. Okay, we have an x squared minus 4, x plus 2. Well, again, focus on the denominator. What do we know? That x plus 2 cannot be 0. We cannot have a 0 in the denominator. Otherwise, it will not work. And so x cannot be -2. Okay, so again in set notation, all x's such that x does not equal -2. Any other x can be placed into this function and you will get an output. -2 cannot go in that function because the result is a 0 in the denominator and you will not get an output for that one. Last example. Example number 5, we're going to take a look at a quadratic denominator. So in this case, r of x is equal to, the numerator is going to be a degree 1 function, a linear function. The denominator is going to be a quadratic function, x squared plus 8x plus 12. Well, how do we know when that's not 0? We need to factor it. Okay, so we're going to factor this. This factors into x plus 6 times x plus 2. And we know this equals 0. Okay, what do we know? Okay, it equals, let me take that back. We know that we want x plus 6 to not equal 0, or we want x plus 2 to not equal 0. So x cannot equal negative 6, and x cannot equal negative 2. So our domain here has two restrictions on it. Okay, we can, again, in set notation, all x's such that x cannot equal negative 2, and x cannot equal negative 6. Let's take a look at that in our calculator and see what's going on with that one. Okay, so I got my calculator up here. I may have to do some zooming. We'll find out. Y is equal to, I've already got my fraction. I'll just press clear and I'll restart. Whoops, hang on a second. Clear, clear. Okay. The numerator is a linear function. Whoops, I lost track of my fraction bar. There we go. X plus 6 in the numerator. The denominator x squared plus 8x plus 12. I'm graphing this one. Let's see here. I may be too far with my window. Let's come in a little bit. Let's go from negative 10 to 10 on the x-axis. Can't be, so there's the negative 2. What's going on with negative 6? Let's take a look here. Okay, second calc of value, and let's put in negative 6 and press enter. Yep, we didn't get the value here, so it looks like what negative 6 is providing us with, negative 1, 2, 3, 4, 5, 6, might be a whole as opposed to an asymptote. I'm not positive, but obviously the calculator is not refined enough to show us what's going on at negative 6. Let's zoom in at negative. Let's zoom in. Let's go from negative 7 to negative 6. Let's see if that shows anything. Here's, whoops. I should have gone from negative 7 to negative 5. Sorry about that. Okay, window, negative 7. I want negative 6 to be in the middle. What's going on at negative 6? Here's negative 6. Well, it looks like, I mean, it's not coloring it in, so something's going on there, and that's probably going to be a 0. But either way, we saw with our calc value, these two numbers are not part of the domain. This one turns out to be a vertical asymptote, and something's going on here with this one is probably an open circle at negative 6. So there you have it. Okay, the big deal with rational functions is they are not smooth and continuous. They're made up of a polynomial function divided by a polynomial function, so we need to keep an eye on zero denominators when we think about our domain.